Resistor power rating. How to calculate the power a resistor dissipates. Choose the correct wattage rating and avoid overheating. We have seen that resistors are very fundamental in building electric circuits. They are used for limiting current. So an appropriate choice of which kind of resistors or which rating of resistors to use for a particular application is very necessary. Generally, electrical power P is given by I squared R, and that derives from the general formula for power. Generally, power is given by the energy consumed over time. All right, power is equal to work over time or energy consumed over time, right? So in terms of electrical energy, the work done, okay, work done is given by I squared R multiplied by T. This is the formula for electrical energy, energy consumed. Okay, we'll not go into the details of how this is derived. This is also something you must have learned in your basic physics. Okay, so if we apply the general formula for power, which is work done over time, that means in an electric circuit, we can have it that the power consumed P is equal to work done, which is I squared multiplied by R multiplied by T all over time, all over T. So that gives us I squared R. T is going to cancel out, T cancels T. So electrical is equal to power is equal to I squared R, which is the square of the current multiplied by the value of the resistance through which that current is flowing. This gives us electrical power, the power dissipated by a resistor generally. Okay, what is then resistor power rating? Every resistor has a maximum amount of power it can safely handle continuously. Okay, so every resistor you come across has a maximum amount of power that it can, handle safely. Anything beyond that, the resistor may begin to have problems. So when electric current flows through a resistor, the resistor converts electrical energy into heat energy. This heat must be safely removed, otherwise the resistor will overheat, change value, or even burn out. Okay, so resistor actually converts electrical energy to heat energy. It opposes the flow of current in a circuit. So because of that, there's heat energy generated. All right. So, and because of that, resistors have specific power rating. That is, there's a maximum amount of energy per unit time that a particular resistor can consume. Anything beyond that, the resistor will begin to have problem. The power rating is measured in watts. All right. It tells you the minimum, I beg your pardon, the maximum power the resistor can continuously dissipate without damage. So let's look at the concept of power and heat. Every ohm of resistance that carries current generates heat proportional to I squared R. That is what we saw in this introduction here. Okay, so every resistor that takes current is going to have some power dissipated in it as a result of the heat generated, and it is given by this equation. Okay, now the wattage stamped on a resistor is the upper safe limit, not the target value. So for every resistor, there is a power rating that is usually associated. Sometimes it is written on the resistor, sometimes it is obtained from the data sheet that comes with the resistor. Like we have seen that for this kind of resistors that we used in our previous examples that have color codings. This kind of resistors, usually you don't have anything printed on them, all right, because of their sizes. That's why these color codings are used. So for a resistor, you cannot use the color codings, all right, to tell the power. You can't read the power rating of the resistor from the color codings. That's one thing to note. It is only the size of the resistor that can make you, know what the power rating is. The smaller the resistor, the smaller the power rating. Okay, and many times there is always a data sheet, all right, that can tell you the rating of that particular resistor. So what we are saying here is that that rating is a maximum power. So on a resistor, if we say that a resistor's power rating is, for example, 2 watts, this is just an arbitrary example now, all right? What we are saying is that this is the maximum, all right, that that particular resistor can take. Anything beyond 2 watts, the resistor will have problem. It does not mean that that 2 watts is what the resistor should operate upon, but it should not go beyond 2 watts. Many times it should not even go close to 2 watts. All right, as we're going to see very shortly in this discussion. Okay, so when this power rating is exceeded, I beg your pardon, the resistor will become damaged. So exceeding the power rating causes permanent drift, insulation failure, or fire. That is, the resistor is going to burn out. Okay, so I have stated that the power rating of resistors cannot be read off the color bands. All right, the color bands only tell us the value of the resistor and the tolerance value. The power rating, on the other hand, is obtained from the size. So the bigger the resistor, the more the power rating. So the physical size of resistor versus power rating, we have some standard power ratings, all right? We have 1 over 8 watts, 1 over 4 watts, 1 over 2 watts, 1 watt, 2 watts, 5 watts, and then maybe we have about 10 watts, 25 watts, and like that and like that. So these are some of the standard power ratings for resistors that we're going to be coming across. Okay, so the larger the physical size, the more surface area, the more heat it can shed, the more heat it can dissipate. That's why we say that the power rating of resistors is, you know, obtained or is determined by looking at their physical sizes. All right. Okay, before proceeding, it means that if we have, let's take this example again. This resistor here is 47 kilo ohm. By now, we already understand how we obtain this 47 kilo ohms. So you can have this color band for a resistor that looks bigger, all right? Maybe you now have a resistor that looks um bigger in size, all right? You have a bigger resistor looking like this. And then you now have, you still have your yellow, you have your yellow as the first color band, and then violet, this is not very clear, and then maybe orange, and like that, and like that. So what I'm saying here is that if you have a resistor that is bigger in size than this, but has this exact color band, it is still going to be 47 kilo ohm. The only difference now is that since it's bigger, the power rating is going to be more. All right. So the power rating can be calculated. All right. I beg your pardon, the power consumed by a resistor can be calculated using this general formula that we have seen. P is equal to IV. And this formula can be stated in 3 ways, just like Ohm's law can be stated in 3 ways. If we say P is equal to IV, P is equal to IV, and from Ohm's law, we know that V is equal to IR, right? By the time we make substitutions, it means that P is equal to I multiplied by IR, all right? And that gives us P to be equal to I squared multiplied by R. I squared multiplied by R. Okay, so the first formula for power that we wrote earlier on is that P is equal to I squared R. And then we derive that through the approach of knowing what electrical energy consumed is per unit time. Okay, so if we import Ohm's law here too, okay, we know that V is equal to IR from Ohm's law. V is equal to IR, right? Now, by the time we import that here, we can say R is equal to V over I. If we decide to substitute this into this formula here, P is equal to I squared R, we can have it as P is equal to I squared multiplied by R, which is equal to V over I in terms of Ohm's law. So by so doing, one of these I takes care of this. And then we have it that P is equal to IV, right? P is equal to IV. So this is another equation. You can see that these equations for calculating power, there are three of them. They are interrelated based on Ohm's law. So the three forms which you can express the formula for power are P is equal to IV, P is equal to I squared R, or P is equal to V squared over R if you make the substitutions appropriately based on Ohm's law. Okay, so each of these formula can be used to calculate power in any way, depending on the parameters you are given. It means that in a particular question or in a circuit, if you know what I and V is, you don't need to want to use I squared and R. You can just use IV and you get the power. If what you are given is I and R, then you use I squared R to calculate the power. And then if what you are given is V and R, you use V squared over R to calculate the power. Okay, the V squared over R can also be obtained in this manner. If you know that P is equal to IV like we've seen, or P is equal to I squared R, depending on the substitution you are making. Okay, if we make a substitution for V here, okay, we can say that beg your pardon for okay, P is equal to IV, right? So V is equal to I is equal to V over R from Ohm's law. Alright, from Ohm's law, I is equal to V over R. I is equal to V over R. Okay, I is equal to V over R. If we put that into this equation, we can have it that P is equal to V over R, which is I now, multiplied by V. And that gives us V squared over R. So these are the equations for calculating power. A quick examples are attached there. For example, if you know V to be 12 volts, I to be 0.5 amperes, what you are given is I and V. So you can just go straight ahead and use this. All right, same thing goes for the next example. If what you are given is I and R, you just go straight and use this. Or if what you are given is V and R, you go straight and use this. Which each of this formula, any of them can be conveniently used to calculate electric power. Okay, here's a quick example. Calculating the power dissipated in a resistor. You are given the resistance to be 330 ohms. You're given the voltage supply to be 12 volts. And then you want to find the power dissipated in the resistor. So you already know R and V. R and V. So it is convenient to use power is equal to V squared all over R. Alright, so that's going to give us 12 squared all over 330. 330. So the power in this case is going to be equal to 12 squared over 330 gives us 0.0436. Beg your pardon, 0.436. 0.436 watts. So the unit of power is watts. Okay. And this is equivalent to, if you convert it to milliwatts, you can have it as 436 milliwatts. 436 milliwatts. Milliwatts. So that's a simple example on how to calculate the power dissipated in a resistor. Okay, any of those three equations can be used depending on the parameters that you have available to you. Okay, so talking about standard power ratings, like we've seen, that the power ratings cannot be obtained from the color bands. right? Power rating cannot be obtained from the color bands. The color bands only tell us um, the nominal value of the resistor and the tolerance. Power rating usually is observed from the size of the resistor. Bigger resistors usually have bigger power ratings. That means they can consume more power because they have more surface area to take in more energy. Okay, so for standard power ratings, we can have um, resistor come in fixed wattage steps. All right, always choose the rating above the calculated power. In your laboratory, in your experiments, you'll be choosing resistors, all right, to build some circuits or to build some simple demonstrations. It's good to know uh, which resistor to choose for which purpose. So some standard power rating that we have is 1 over 8 watts, 1 over 4 watts, 1 over 2 watts, 1 watt, 2 watts, 5 watts, 10 watts, 25 plus watts. This information usually is gotten from the data sheets that accompanies the resistors, all right, or the information that comes with the resistors, and also by observing the sizes. So for very low power rating, power rated uh, resistors, they are used for signal and low power circuits, microcontrollers. Usually these resistors are of this size, 3.5 millimeters long. And then we have the 1 over 4 watts, most general purpose uh, through hole circuits. These are their sizes typically. So it is with experience that you can look at the size of a resistor and tell the power rating. At this level, or at the beginning, you might need to consult the data sheets or the documents that comes with the resistor, all right, to be able to know what the power rating is. But with time, as you get to work with resistors over and over again, experience makes you to know or to be able to get the likely power rating of a particular resistor based on the size. You can see that the bigger the size is, all right, the more the power rating. You can see that a 25 long resistor has is rated 5 watts, but a 9 long resistor is rated maybe 1 over 2 watts, which is 0.5 watts. All right. So these large resistors, beg your pardon, these higher power rated resistors are used for higher power industrial loads and circuits. Okay. Now for SMD resistors, for surface mount resistors, all right, they follow a different code. They don't follow these resistors. Typically this kind of resistors are maybe metal wound resistors or carbon film resistors. Those are the ones that usually come in these formats, all right, that has a color code on it, like we have seen. But for SMD resistors, surface mount resistors, they are coding it. They follow a different convention. Okay, you are going to see a number on it. You might not be dealing with much of the SMD resistors at this beginner level, but you're going to see a code on it. That code, tells you what the power is. Just like in a very previous discussion, we said that the SMD resistor looks something like this. You can see that there's this code on it, 0.603. This code tells you the power rating, and it is not expected that you try to memorize this power rating based on this number. If not, you are going to have to memorize a lot of numbers against power ratings to be able to tell what the power rating of a particular SMD resistor is. Data sheets, all right, and documentation usually come with some of these uh, resistors that you can easily reference. So when you look at an SMD resistor and you see this color code there, you just try to consult a data sheet based on the IEC standard, and it will tell you what the power rating of that particular resistor is. Okay, so SMD resistors follow a different pattern to be able to decode their power ratings. Okay, now how do you now choose a resistor in a circuit? So we're going to look at choosing a resistor in a circuit. When choosing a resistor, you follow what we call the derating rule. That is, choosing the safe rating for the application that you want to build or the experiment you want to carry out. If uh the resistor you choose is not properly chosen, by the time you want to, maybe you have finished building your circuit and then you power it, at the end of the day, the resistor may begin to have problem. So the rule here is that never run a resistor on its maximum rated power. Use the 50% derating rule. All right? Use the 50% derating rule. Okay, what does that mean? It means that if you have a particular resistor rated, for example, 2 watts, all right, this is the rated value of the resistor. You are not permitted, or it is not advisable you run the application such a way that it is going to consume up to these 2 watts, which is the maximum rated power. Remember that we said that the ratings stated are the maximum value they can take. So you are going to use it such that you have to consume, it won't have to consume up to 50% of this rated power. That is what we call the resistor derating rule. Why do we derate? A resistor run at 100% of its rated power runs hot, has shortened lifespan, and may drift significantly from its nominal value. In real-world design, engineers apply the derating factor for reliability. So you don't use a resistor to its full capacity in terms of the power rating. It's going to have problem. Okay, and you know the rated power now should be greater than or equal to the actual power divided by the derating factor. This is the formula to use in derating, you know, in determining, I beg your pardon, the resistor to safely choose for a particular application. Okay, so the rated power should be greater than or equal to the actual power, all right, divided by the derating factor. For most resistors, the derating factor is 0.5, which is it should not run more than 50%. The power consumption should not be more than 50% of the rated power. The rated power is what you have on the resistor. The actual power is what the resistor is intended to actually consume in reality. Okay, so if we do that now, we are going to see that the rated power, P rated, all right, should be greater than or equal to the actual, that is what it is expected to consume in the circuit, the actual power, all right, actual power divided by the derating factor, which is usually 0.5 for many applications. All right, so you can see that if we do this, this is like saying the rated power now, okay, should be greater than or equal to 2 times the actual power. 2 times the actual power, because any figure over 0.5 is like 2 times that figure. All right, the actual power. So when choosing a resistor, this is taken into consideration. All right, calculate the actual power that is meant to be consumed in the circuit using any of the equations that we have seen. Then apply the minimum derating. All right, apply derating. That is the minimum rated value must be equal to or greater than, you know, 2 times the actual um, power that is going to consume. Okay, then you pick the net standard rating equal or above to that minimum. If operating in a hot environment, all right, apply an extra derating. So I'm going to explain this through an example that we're going to see shortly. Okay, so what we are saying here now is that if what you need, what you want to consume in a circuit is maybe 3 watts, for example, by the time you check the table of standard resistor ratings, you're not going to see 3 watts. Okay, you're going to see 1 watt, 2 watts, 5 watts, 10 watts, and the likes. So if what if the power that the circuit is going to require is 3 watts, you have to now check against the standard, power ratings that is available and know which resistor that you are going to choose. So here, you either choose 5 watts or 10 watts, something higher. In the circuit, if what is going to be consumed is 2 watts, from this derating factor that we have seen, it will not be advisable to go for a 2 watts, because if what is required to be consumed in the circuit is 2 watts and you are choosing a 2 watts, that means you are trying to, apply 100%. All right. And that's not going to be good for the resistor. So you have to now go for something that is higher at least. So you still go for a 5 watts. Okay. Let's look at this example. You have a resistor, right, that is given by 47 ohms in value. Then the current in that circuit is 45 milliamperes. And then the question is, what power rating is needed? So in a circuit, the resistor is 470 ohms, the current flowing is 45 milliamperes. All right. You are now asked to choose the resistor for this circuit. All right. The actual power that is needed. I beg your pardon. You're supposed to choose a resistor that will suit this purpose in this circuit. Of course, there's a resistor already, but which one, which power rating you are going to use? Like I said earlier on, that you can have a 470 ohm resistor that has different power rating. I cited an example with the 47 kilo ohms here, right? We stated that this 47 kilo ohms, you can have 47 kilo ohms that is, um, I'm just giving just for illustration purpose now. You can have a 47 kilo ohms that is 2 watts, for example, all right? That is 2 watts. You can have a 47 kilo ohms that is 5 watts. So the wattage of the resistor is entirely independent of these color codings. The only thing that will make you know which one is 2 watts and which one is 5 watts is that which is 2 watts, all right, is going to be smaller in size. Why that which is 5 watts is going to be bigger in size. So you can have a particular uh, resistor of a particular ohm value, all right, that has different sizes. Okay, and those different sizes, you know, tells you that those are the different power ratings that are available based on the information that comes with the data sheet or the documentation. So in this example, what we have here is that we have a 470 ohm resistor, all right, and then the current that is going to be flowing through that circuit is 1 I beg your pardon, is equal to 45 milliamperes. So which power rated resistor now, or which power for that resistor we are going to be choosing? I beg your pardon. Um, okay, let me check something very quickly. Okay, so which power value, let me put it that way, are we going to be choosing for this particular resistor? That's what we want to see. So we apply the derating rule. In applying the rating rule, the first thing you do is to calculate the actual power that is expected in that circuit. We are giving R, we are giving I. So we know that the power P is equal to I squared multiplied by R, right? I is given in milliamperes here, so it must be converted to amperes, which is 0.045 amperes. By the time you do that, and you multiply it by R, which is in ohms, you're going to be having the power here to be equal to, power is equal to I squared 0.045 squared multiplied by 470 is going to give us 0. Let's check that. It's going to give us 0.952 watts. Right? By the time you calculate that, you're going to have 0.952 watts. Okay, 0.952 watts. 952 watts. Okay, so this is the actual power that is going to be consumed in this circuit. If I want to now choose a resistor, all right, of this value against a power rating now, I will have to now apply the derating rule. And the derating rule states that the P rated now, the rated power, all right, P rated must be, beg your pardon for space, I'm just trying to, constrain my writing here, okay? P rated must be greater than or equal to 2 times the actual power that the circuit requires. All right, 2 times the actual power that the circuit requires. So the actual power the circuit requires here is 0.952 watts. By the time you multiply this by 2, okay, you're going to be having, this is actual now. So by the time you multiply it by 2, you're going to be having 1.904 watts. So this means that the rated resistor I'm going to choose now, P rated, all right, P rated, P rated, let's write that somewhere around here to be better. P rated now should be equal to or at least greater than or equal to 1.904 watts. So by the time I go to my table of standard resistors, I'm not going to be seeing 1.904 watts. What I'm going to be seeing is 1 watts. All right, 1 watt, 1 over 4 watts, 1 over 2 watts, 1 watt, 2 watts, 5 watts. Those are the standards. Like I said, it's not expected that you keep all these things in memory, except if you begin to work with resistors often and you now have experience. You can easily, recall by inspecting the resistor. So many times you have to refer to some documentation, some data sheet to look at to know what values are available for a particular resistor. So the rated, according to this example, the um actual power that is consumed is this. In applying the derating rule, the rated resistor I'm going to choose, all right, the power for the rated power I'm going to choose should be at least 2 times this actual power. And 2 times this actual power is 1.904 watts. So that's what I'm now going to be comparing with my standard table of resistors. So I want to compare 1.904 watts on this table. I can't find this value on this table of resistors. What I can find is 1 watt, 2 watts, 5 watts. There is 0.125 watts, there's 0.25 watts, there's 0.5 watts, there's 1 watt. So if I choose 0.5 watts, it is lower than this one that I've used the derated factor to determine. So it is safe for me to now choose 1 watt. Is it safe for me to choose 1 watt? No. 1 watt is still lower than this value. All right. Then the next available value is 2 watts, which is greater than this value. So by the derating rule, the rated value chosen should be equal to or greater than, should be at least this actual value. And from that table of values now, we see that 2 watts is what satisfies this um, condition. So if I'm going to choose a resistor now, I will choose a 470 ohm resistor that has this power rating. And I can get that from the documentation available, the data sheet available, and then by also knowing the size of the resistors that are available for 470 ohms, value. Okay,